All right, we'll go ahead and get started. Thank you everyone for being with us this morning as we present a little research that was funded by the New York Wine and Grape Foundation. We have Katie Gold with us this morning, who is an expert in her field, and we're happy to hear everything she has to say. And without further ado, I'll just go ahead and hand it off to her.
Thank you so much, Justin. It's great to be here. Happy Monday, everyone. It's really fun to be able to give this presentation today about our fungus sensing work that's been funded by the New York Wine and Grape Foundation for the past 2 years now. So today I'll be talking about our project that's seeking to build this fundamental capacity for plant protection sensing in order to improve sustainable grape disease management. I'm going to start more broad with the kind of broad themes and theory that inspired this work. Then in the middle, I'm going to get down a little bit into the technical weeds, bear with me, and then we're going to zoom back out for what the vision of this work can be for the grape industry, here in New York one day. So without further ado, let's get started. As Justin kindly mentioned, I guess I'm an expert in my field, right? Here we go. But I like to start with the fundamentals of my field, which is plant pathology. So I'm well known for the work that I do in remote sensing, but at my core, I am a plant pathologist. I've got diseased pictures on my phone that I cherish, I adore. I have my favorite disease, which is downy mildew. Here you'll see featured throughout this talk. And I want to start this talk with the fundamental theory of plant pathology, which is what we anchor all of our work within, which is that disease is a result of complex interactions between antagonistic organisms and their environment. You only get plant disease occurring when you have a virulent pathogen infecting a susceptible host within a conducive environment. However, this theory occurs in managed ecosystems when we're considering grape and New York State viticulture. So human management, this disease triangle, these dynamic relationships happen within this bubble of management, this human interface between disease and the broader world. So human management both impacts disease development and our detection of it. And remote sensing is truly one of the only scalable methods that we have in our disease control toolbox that can transcend historical limitations to provide actionable early warning and detection. My lab has pioneered this holistic approach to plant disease sensing that takes into account all three aspects of the disease triangle, as well as this management bubble that defines really plant disease sensing. So when I say management, I think of the actions that we take upon our vineyard, both to try to prevent disease and in response to finding it in the first place. And all of these impacts disease detection on varying scales. My lab is the Grape Sensing Pathology and Extension Lab at Cornell Agritech. We're funded by diverse sources, including the New York Wine and Grape Foundation, and we specialize in a type of remote sensing called in situ and imaging spectroscopy. This is also called hyperspectral imaging. And we use this technology across a range of deployment scales, from handheld sensors all the way up to aircraft and satellites. Today, I'll be talking about some of our use cases that we're developing at the handheld level in order to begin that scaling process to go from fundamental handheld all the way up one day to the vision of maybe even satellites. Much of our work is conducted within the Cornell Pathology Vineyards at Geneva, New York. We have over 9 acres of vineyards that are used for our disease resistance research, as well as fungicide efficacy trials for a variety of grape diseases such as powdery mildew, downy mildew, black rot, botrytis, phomopsis, and sour rot. This is, we work closely with allied industries. We have over 100 contracted treatments per year, and everything within this vineyard is the hub of our applied disease management research, but also where so much of our more fundamental remote sensing research takes place, including what I'm going to talk to you about today. I would be remiss to not acknowledge the role of Dave Combs, who is my field research manager, who plays a critical role in keeping our vineyards alive, healthy enough, right, for us to do this wonderful work within. So now let's move on. So fungicides are absolutely critical for modern agricultural production, but it's undeniable that their overuse has financial, environmental, and also pathogen resistance consequences. And this is particularly important here in New York as we're dealing with the impact of fungicide resistance much more acutely than we ever had before. On average, it costs about $50 an acre to make a single fungicide application. So if our goal is to sustain and enhance and ensure the viability of the New York grape industry for the long term, we really need to focus on continuous innovation in how we do chemical disease control, as it truly is the bedrock of grape disease management in New York State, given the immense pressure that we face from varying diseases and pests as well. But I want to highlight here the pathogen resistance consequences, as this is what most acutely inspired the work that I'm going to talk about today. Fungicide resistance is a phenomenon that emerges over time with continued exposure. So you'll have an initial population that just naturally has a resistant individual. You expose it to a fungicide that resistant individual can sustain, and over time it will become more populous, greater represented in the broader population. And this problem of fungicide resistance becomes even more acute when you have limited products to use, such as that we face here in New York. So if you only have a handful of products that you can use to control disease, you are simply much more likely to get fungicide resistance over time, because you will be exposing that population again and again and again to a product that it is now able, the population as a whole is now much more able to resist and grow throughout. And this problem is particularly acute in New York viticulture. So in 2020, 2021, we were supported by the New York Wine and Grape Foundation to do a fungicide resistance survey in partnership with the Frame Networks and Michigan State University, where we found that about 70% of Finger Lakes vineyards had FRAC 40 resistant downy mildew. This is Revis CAA fungicides, which was up from 40% in 2020. Additionally, too, we found that about 80% of Finger Lakes vineyards had FRAC 11 resistance. So this is QOI strobilurins, such as Flint and Quadris. This is particularly challenging for downy mildew because downy mildew is an omycete, which means that we technically need to use specialty omicides to control it, of which we have far fewer in number than we have other fungicides that control true fungi, such as powdery mildew and black rot and botrytis as well. So we're facing a growing problem with fungicide resistance here in New York. When we consider the pillars of fungicide resistance management, it settles on this foundation of knowing the risk factors that encourage the development of fungicide resistance. But there's really two core pillars that hold up this fungicide resistance management. The first of which is early detection, so you can take early action. But the second, which I'm going to focus on today, is this idea of proactive prevention, preventing fungicide resistance from happening in the first place. So in learning about the grape industry back in 2020, I knew it was possible to do disease detection, but in trying to getting to know the grape industry here in New York, I realized how critically important it would be to, just as much as knowing where disease was, to understand where protection was still active. Because if grape growers knew where and when fungicides were still active, they could make more strategic decisions on what, where, and when to spray to control disease. And this would greatly improve the useful livelihood of the fungicides that we rely on for disease control and slow the tide of fungicide resistance development. If we were able to do more strategic intervals, optimize interval length, if we knew that fungicide was still active, we could take a longer time between sprays, or we could take a shorter time between sprays when necessary and in the areas where necessary. Additionally, understanding the longevity in field and near real time would allow us to make more strategic decisions about what we spray. For example, if you know that there's no disease pressure and that you currently have active fungicide, but you still want to provide additional protection, you might feel more empowered to use a lower active, such as a biopesticide. Overall, this would reduce the risk cup and the overall exposure of our pathogen populations to these fungicides and therefore slow the tide of resistance development. So now we're going to start getting into the more technical stuff of the approach that we're taking to build this capacity for plant protection sensing. And I want to zoom out for a moment and just talk a little bit about the fundamentals of how this technology works and why it is so applicable for fungicide sensing. So spectroscopy has wonderful, absolutely wonderful applications in agriculture because of the nature of how light interacts with plants. Plants are designed by nature to engage with the sun. For example, light will enter our atmosphere from the sun and will do one of three things when it hits a plant. It will be absorbed for photosynthesis, it will be transmitted through, or it will be reflected back. And the bulk of light that interacts with the plant is actually reflected back. And this light can be quantified by a sensor as distantly placed as a satellite in space. And plants are they're designed by nature to take advantage of these light interactions, which is what makes sensing such a useful technology for agriculture and plant health in general. But now when we consider how the light is reflecting, this is how we're able to derive from that information such important and exciting information about plant health. So when we consider a leaf, if it's working properly, it's going to be nice and healthy and green, right? It's going to be photosynthesizing. This means that it's going to be absorbing a lot of blue and red light for photosynthesis and reflecting back a lot of green light because it's going to have a lot of chlorophyll. It'll be nice and healthy. This healthy leaf will have a good, robust structure, so it will be reflecting back a wealth of near-infrared light, which the plant does not use for any of its innate purposes. Now, when a leaf is unhealthy, it's not going to be photosynthesizing properly, so it's going to be reflecting back more red light. This means if it's not photosynthesizing properly, it's going to have less chlorophyll, and it's going to reflect back less green light. This unhealthy leaf is going to have a more compromised leaf structure, and therefore reflect back less near-infrared light. So how the light is reflecting off of a plant will tell us that information about the plant's health. And this is because spectroscopy at its fundamental level is able to measure plant chemistry. And it can measure a number of different things about plant health as relates to plant chemistry, such as drought stress, nutrient stress, and disease. And it is able to do this because it measures light beyond the range that which we can see. So if you think for a moment about every color that you've ever seen in your life, just the richness, the gradation, the variation, all of this comes from a wavelength range that's about 300 nanometers wide. The sort of sensors that we work with for this project see 2,100 different wavelengths. So that's 7 times as much light as our eyes can see. And this light, it's less abundant in our atmosphere, but it very precisely interacts with aspects of plant chemistry. That's why we're able to use it to measure all these aspects of plant health. So hyperspectral sensing can precisely measure environmental chemistry. This is the utility that was established by the forest ecologist over the past few decades that is formed the foundation for this revolution in plant disease sensing that eventually trickled down into the Gold Lab, of course. So when you take a hyperspectral reflectance curve, such as the one that I'm showing here on the left, and you combine this with various statistical approaches or machine learning, you're able to turn that little number string into a near direct quantification of a variety of chemical properties of plant, such as the exact amount of nitrogen, the leaf mass per area, the total amount of sugars, starches, chlorophyll, pigments, the water within a leaf, as well as various micro and macronutrients. You can also measure compounds that relate to decomposition, such as lignin, cellulose, and defense, such as phenolics and tannin. So we understood this capacity very clearly for hyperspectral sensing, but what we wanted to know was, well, if this technology works so well for natural chemistry, could it also measure synthetic chemistry, such as the fungicides that we apply to our leaves in agriculture? From the core, it seems, well, there's no reason why not. So now I'm going to talk about the work that was initially supported by the Wine and Grape Foundation, as well as the New York Farm Viability Institute that supported my lovely postdoc, Dr. Nikita Gambhir, who is a postdoc with my program from 2020 to 2022. She is now a discovery scientist at FMC. So what we hypothesized was that when you apply either a protective or systemic fungicide to the leaf, to a plant, that it will change how light interacts with that leaf, both the externally reflected light as well as the internally reflected light. So we thought that, well, if we can measure natural chemistry, there's no reason why not. We could measure the synthetic chemistry applied both for a protective surface level fungicide as well as a systemic fungicide that goes throughout. So we designed an experiment that would take place in both the field as well as the greenhouse using 3 different types of fungicide. We used a synthetic fungicide called metrophenone. The trade name for this is Vivando, as well as a biofungicide, Bacillus mycoides isolate J, the trade name for which is Lifeguard. This is a biofungicide that works by activating the plant's defenses. We applied this with a tractor tractor-pulled fungicide sprayer, covered boom. And we also applied sulfur to leaves in the grapevine leaves in the greenhouse in 2021, as well as 2022. And these intervals, and we applied these fungicides at 14-day intervals in both the field and the greenhouse. Next, we captured in situ leaf reflectance with our handheld spectrometer. So this box is the Cadillac of in situ spectrometers. This is the finest and most precise level of sensing you can do because there's the least amount of interference from the atmosphere and other aspects between it. So if this capacity was not possible at the leaf level, we simply it could not be possible at any other level. So we measured leaf reflectance with the handheld spectrometer both in the field and in the greenhouse at 2, 5, and 7 days post-application for 80 leaves per treatment, once again, both in the field and in the greenhouse, but at slightly different intervals. The leaf samples were then collected and transported to the lab on ice, and I want to acknowledge here the role of Nikita, my lab manager, Angela Paul, as well as Ugo Ikeogu, who was a postdoc with Bruce Reich at the time. From there, what we did was we took advantage of the VitusGen Blackbird imaging system in order to measure different aspects of fungicide activities. We took from our leaves and we punched discs from each and put them onto an agar tray so that they could be imaged. The trays were inoculated with Uracipy necator, which is the causal agent of powdery mildew, and then imaged over the course of 11 days with the Blackbird to measure how much disease developed. We then additionally sent 7 discs from those leaves that we sampled to have the fungicide amounts quantified precisely. So the fungicide concentration on the leaf precisely quantified with liquid chromatography mass spectroscopy. This is LCMS. So with this, we were able to measure 2 different aspects of fungicide activity. One, fungicide control efficacy, so how much disease developed as or did not develop as a result of the fungicide, as well as the exact concentration of fungicide on the leaf. And what we found was that the wavelengths that were important for discriminating between the treatments, which were once again a synthetic fungicide, a biofungicide, and a protective fungicide, a synthetic systemic fungicide, systemic biofungicide, and protective fungicide varied across the different treatments and were found throughout the visible range, the near infrared, and the SWIR range. So remember, the visible range is the only range that we can see. And we would suspect that if fungicides were active and our capacity for detecting them was simply based on the physical presence of them, such as when you spray a fungicide, you'll see the residue on the leaf, that would be represented in the visible range. However, if we saw that the SWIR range were important, this would give us evidence that it was not simply just that visible residue of the fungicide that was contributing to this capacity, but the actual bonds of the fungicide were helping us distinguish between leaves that had been treated and leaves that were untreated. So across all 3 that we measured, we found that the spectral curves were significantly different from each other, and that with great accuracy and reliable accuracy, we could differentiate between them. So we used a statistical method called partial least squares discriminant analysis, which is really well suited for measuring, for working with spectra, which is complicated, unknown correlation structure, and it's a very well-used method. And we found that the spectra of all 3 of the fungicide-treated samples, the 3 different types of fungicides we used, could be differentiated from the untreated leaf samples with high accuracy across all time points studied, across all of them been together, as well as across 2, 5, and 7 days post-application, as well as for sulfur at 3, 6, and 10 days post-application. And that these accuracy ranged from about 70-ish% all the way up to 97% for sulfur. We additionally calculated a metric called kappa, which is basically accuracy that adjusts for random chance. And all of these kappa were quite accurate, quite high for kappa, which made us very confident in that fundamental ability of our system to be able to measure or distinguish between leaves that had been treated and untreated with fungicide. So for context, anything above 0.4 for kappa is considered good. Next, we wanted to look into those two different measurements that we made that account for fungicide activity. The first of which was control efficacy, right? So fungicides provide disease control. That's the whole point, right? We want them to stop disease development. So we hypothesized that we could measure how well the fungicide was controlling disease by measuring the inverse of how much disease actually developed over time. And we found that yes, this was indeed possible. Across all time point study, I present here both the metrophenone, which is your Vivando, and the Lifeguard. We were able to predict the control efficacy of the fungicide from the spectra alone with reasonable, modest R-squared values. We also saw that this varied across the different time point study. For example, at 2 days post-application, we found that our accuracy was the highest, which is what you would expect. 2 days after you apply your fungicide, you're most likely going to be getting your strongest response. So we saw that yes, check mark. We can distinguish between leaves that were treated and untreated with high accuracy, and we can predict the amount of fungicide control that fungicide present on the leaf could provide to the leaf. We next wanted to assess that second aspect of fungicide activity, which is the exact concentration, right? So there's the goal of the fungicide, which is control disease, right? Like that's an outcome, but also the amount of fungicide presence also has a very important role in determining its activity, its longevity, its degradation, survivability in the environment. And we did this for both metrophenone and sulfur. And we found that with sulfur, we could predict our concentration with a reasonable R-squared of about 0.4. And we could also do the same with metrophenone, though with a little less precision there. So we were pleased. We were able to do that second checkbox of yes, not only can we can measure two different aspects of fungicide activity, both the fungicide control provided by the fungicide and the amount of it left. So in summary, we were able to establish these three different use cases, right? We could use spectroscopy to one, say whether or not a leaf had been treated with 3 different fungicides with 3 different modes of action. We could measure the control efficacy provided by that fungicide, as well as the exact concentration of the leaf. So when we consider the story so far, we found one, spectra of those fungicide-treated samples could be differentiated from the untreated samples with high accuracy for 3 fungicides with different modes of action. That was really important. We wanted to look at this across the different modalities of fungicides that we have. The second is that we saw that wavelengths that were important for discrimination were spread across the visible, near infrared, and the shortwave infrared regions. This is important because the fact that shortwave infrared regions as well as near infrared regions were important for discrimination means that it's not simply that visible residue of the fungicide contributing to our capacity, it was the actual interaction of light with the fungicide bonds themselves, because SWIR and near-infrared wavelengths correspond most closely to environmental chemistry and not just simple visible, interaction of pigments. And finally, our preliminary results from Gambier et al. 2023 indicated that spectral prediction of both control efficacy and fungicide concentration was possible with modest R-squared values. Now, this was pandemic era science. It took a vast team to put together. We were also working with small numbers, given that we had restrictions in place from Cornell about how many people could be working together at a given time. So with these promising results, we wanted to scale things up. So I'm now going to zoom back out for a moment to the vision of what this technology could be in the vineyard one day. So we established that fungus sensing, right? Excuse me, is indeed possible with handheld spectroscopy. However, handheld spectroscopy is not something that any sort of grower might use one day. Its real utility is in proof of concept. For this technology to truly be applicable one day, we have to begin scaling towards more passive degrees of monitoring, such as drones, aircraft, or maybe even one-day satellite. However, our target for this is drones. Additionally, we came up with a vision of how a grower might use this information to make a decision. For example, we know very well that that we can use spectroscopy to detect disease or not, right? But so if we were able to use it to say, okay, there is disease here or not disease here, and there was also low fungicide, this would encourage the user to apply a strong active, such as something that is potentially resistant prone, but known for its activity. However, if there is disease and a high fungicide present, depending on that decision maker's level of comfort, right? They might make a choice to not spray at all and just rely on the fungicide that they had sprayed previously, or they might spray an additional low active. For example, something like a biopesticide or a traditional chemistry that just has lesser efficacy against, but is less resistance prone because they knew that they still had high fungicide that was active from their previous spray. Now, if we consider the lower half of choices, such as, okay, we don't detect any disease, but we do detect low fungicide, this might encourage a grower to make a choice to either spray a low active, something that is maybe a traditional chemistry that has activity, like established activity upon it, but it's, it's not the best, right? So it's no methanoxam, right? Or depending on their comfort level, maybe make no spray at all. It just depends on what their goals are for their vineyard. Now, if we have no disease and high fungicide activity, this would encourage that decision maker to choose not to spray. They would feel comfortable in that decision to keep letting that interval ride out. This would improve, once again, the overall financial, environmental, and sustainability of our industry, and importantly, slow the tide of resistance development, because we could save our usage of those high resistance prone chemistries for only 1 out of these 4 use cases. Whereas right now we have no information about any of these use cases. So we're using potentially, 3 times more frequently than we necessarily need to. But for this vision to become a reality, we need to focus on enhancing the throughput of our methodology, scaling up from our pandemic era numbers, as well as focusing on scaling through the vertical scales of remote sensing, going from handheld level to more distant and more distant forms of sensing. So with this, we've been using the Hyperbird. This is a collaborative project that's between my lab, Yu Jiang, who's another assistant professor at Cornell Agritech, the closest thing one could have to a best friend in academia for me, as well as Dr. Lance Cadle-Davidson of the USDA ARS and the VitusGen program. The Hyperbird is a hyperspectral imaging robot that collects hyperspectral images with 1 nanometer resolution, and it's able to scan 350 samples in only 4 hours. In contrast, one postdoc can scan, I think maybe 100 samples in 4 hours, and it produces 3.5 gigabytes hypercube per data. So it's very rich. It's very exciting for the engineers and the technology wizards, the sort of data that comes out of it. And it has 4 different things that comprise it. It has a push broom hyperspectral camera. It has a high intensity custom designed light to make the best and such that we get the best and most clear quality data back from it. And it intakes a tray's worth of data. So if you remember back to that methodology that we were using, this is adapted from the Blackbird system. So the same tray that we were able to put into our imaging robot, we can put into our hyperspectral imaging robot. And it has, of course, that robotic base platform. And we've been building out the utility for this robot for 3 different domains. 1, fungicide quantification, which I'll talk more about. 2, disease detection, as well as 3, breeding phenotyping for the grape breeding program here at Cornell. So after my postdoc Nikita left, I was very fortunate to be able to take Dr. Saeed Hossein-Zada onto my program. He graduated from Cornell with his PhD in plant pathology from Dr. Michelle Hack's lab in 2022 and joined my program earlier this year as a postdoc on this project, and supported by the New York Wine and Grape Foundation. And he developed this really clever pipeline for enhancing the throughput of this utility that we've established at the handheld level to begin that scaling, that vertical scaling process, as well as horizontal scaling to assess more samples and more treatments. And here's just a couple examples of his preliminary results doing this sort of work. What he wanted to explore as well was diving more into the different types of systemic chemistries to see if we could detect and distinguish between QOY fungicides that were to build a common model, such as, yes, this is a QOY, or specific models that say this is this type of sensor. So that's like, can we build a model that says, yes, you have Flint Quadris, any other one active, or models that say you only have Flint active? And thus far with the new system, He's been getting some really excellent results with this higher throughput. We've been able to enhance our numbers to get more clean information about what we're seeing with less noise from the environment that we unfortunately dealt with during the pandemic due to personnel kind of restrictions. There's a lot of time between sample collections. We're able to do things with much more precision now. So these are results from our handheld spectroscopy with the throughput increased, and we're still analyzing now with our Hyperbird system. But overall, we're quite happy with the level of accuracy that we're now seeing for this system. Now, thinking more about the vision for what we want to do next, my program as well has been doing a lot of research on applied grape disease control with both conventional and biopesticides. My predecessor, Wayne Wilcox, for over 20 years, had done numerous fungicide efficacy studies, which I inherited when I took over the program. And since, with the help of my field research manager, Dave Combs, and lab manager, Angela Paul, have expanded to encompass from 3 to 6 different disease studies. And we've really been focusing on the use of and the timing of biopesticide products to try to do more proactive prevention of fungicide resistance development, to reduce that overall pressure we're placing on our highly effective but highly resistant prone chemistries. So to enhance the longevity and the useful livelihood we have out of these chemicals for disease control in New York State. So we've been doing this work in our fungicide resistance trials, and meanwhile, in Nikita's work, we saw that non-destructive plant trait indices were able to measure significant differences between the biofungicide and the untreated samples. So as I mentioned, hyperspectral sensing can quantify environmental chemistry. And when you use a combination of statistics and machine learning, you can turn those little reflectance curves into near direct quantifications of various plant traits. So when we did that, we saw that when we looked at the lifeguard treated and the untreated samples, we saw that leaf mass per area, nitrogen, and total phenolics significantly differed between treated and untreated across the entire time period studied. In particular, we saw that phenolics was always different between lifeguard and untreated leaves. So we now have been, as we're thinking about the next generation of our biopesticide research, one thing that we've noticed is that biopesticide performance is pressure dependent. In low pressure years, we see that our biopesticides are able to provide equivalent control to our conventional chemistries. However, in high pressure years, we see that both our biopesticides and our conventionals fail. So I guess one could say that no matter the pressure, biopesticides are now capable of providing equivalent control to conventionals. However, there's still so much that we don't know. For example, we don't yet know about the best biopesticide and conventional mixes, as well as, very importantly, how does timing of application impact their efficacy, as well as does having any sort of varietal/disease susceptibility make a large impact on efficacy. So we're hoping that fungus sensing can help us answer these questions, both by detecting the active chemistry for the conventionals, as well as the influence of the biopesticide on plant health. So this is a picture of our newest vineyard, our traminettes. These were established with the support of a New York Wine and Grape Foundation grant in 2021. They're now reaching maturity, and we're really excited to launch our new trial next year, where we're going to be working out some of these more applied disease control questions in concert with our more fundamental fungus sensing questions. So now returning to this idea of the pillars of fungicide resistance management, early detection of resistance is critical, but so is proactive and prevention. So we're hoping in the future to attack this proactive prevention with this two-pronged approach, really building out the utility and our understanding of how best to use biopesticides in a disease control program to reduce the overall pressure we're placing on our conventional chemistries such that their useful livelihood is extended and we can rely upon them for disease control at the critical periods for decades to come. By reducing the amount of exposure our pathogen populations are getting to them. We apply less of them per year, the longer we'll be able to apply them. Additionally, with our fungus sensing, we're hoping to be able to one day, the vision is provide decision makers, provide growers with the information they need to truly make strategic decisions about what, where, and how to spray. whether or not you have disease, as well as what is the amount of your fungicide that is still active. With these two core components together, we hope that our stakeholders will be able to make fully informed decisions about sustainable management. So just some take-homes from the overall webinar. First, hyperspectral sensing can detect fungicides on grape leaves, and the spectra of fungicide-treated samples could be differentiated from untreated with high accuracy for multiple fungicides with different modes of action, from surface protectants to systemic to biofungicides. We saw that the wavelengths important for discrimination for these treatments span the whole range measured, from the visible to the shortwave infrared. So it's not simply the presence of pigments on the leaf surface from the fungicide residue, it's actually the influence of the actual fungicide bonds that contribute to this capacity. And finally, we hope that precision management informed by hyperspectral measurements could one day help reduce fungicide resistance emergence through more strategic fungicide application. And we're very grateful to the New York Wine and Grape Foundation for supporting this holistic research. And with that, I will now, if I have time, take any questions from the audience. I'd like to thank, of course, my two postdocs that have been doing excellent work on this project, Dr. Nikita Gambier, as well as currently Dr. Saeed Hossein-Zada, as well as Dave Combs and Angela Paul, who manage our field research program. So I can go ahead and read the Q&A, okay? So I have a question from Ryan Fessenden. The question is, can these sensors distinguish disease problems from nutrient deficiency? That's a great question. So at a fundamental capacity, yes, we can. The question is usually, can we do this at scale, which is still kind of an uncertain. So when we're working at scales of sensing that are the closest to the leaf, such as the leaf itself, or very kind of close to it, physically close to it, like, sensor plant kind of physical closeness, yes, we can absolutely distinguish between disease and nutrient deficiencies. But as we scale up and there's more interference from the environment, the atmosphere, and sensing, it becomes more complex to distinguish between disease and nutrient deficiencies, especially when that underlying, because what drives that ability is the underlying physiology. For example, if a disease is causing the plant to have less nitrogen, that could be more difficult to distinguish from a nitrogen deficiency. However, what we have seen in the literature that even when there are visibly identical symptoms, such as wilt, right? One that's caused by drought stress and one that's caused by a disease, because those wilts manifest from different biological origins, we are able to distinguish between them. So if a nutrient deficiency and a disease are manifesting from different biological origins, we should be able to distinguish between them at scale. So we have, we're kind of in the proof of practice mode for that sort of work. And my wonderful student, Kathleen Canale, is starting to work out some of these problems. The next question is it possible to use this technology in virus detection and sprayer coverage? So for the first part, yes, absolutely. My student Fernando Romero Galvan right here, he's been doing outstanding work using aircraft-based hyperspectral sensing to do asymptomatic viral detection in vineyards in California. And my student Kathleen Canale is looking to scale this technology to New York State using UAV-based hyperspectral sensing. In terms of sprayer coverage, there's kind of no reason to suspect why it couldn't do this. It's the same sort of capacity, right? That because if the sprayer is covering it with the chemistry, we just haven't assessed that yet. But I would guess based on the fundamental science that this would indeed be possible, as long as your sensor is getting information at an appropriate scale, right? Like this is not going to be possible from a satellite level. It's very likely going to be possible from a UAV level.
It's really exciting to see the potential of not only integrating, and determining the effectiveness of these biopesticides on a vineyard-wide scale, but also the applications just for reducing and understanding. It's exciting to say the least, and I think it's something that's been dreamed about for a long time in all agricultural sections.
Thank you. Yeah, we're really grateful for the Wine and Grape Foundation's support to try to answer these questions and build towards this long-term vision.
Well, and it's great in New York where our climate makes us so heavily dependent on fungicides when we're pushing towards a
Exactly.
more sustainable industry throughout. I mean, this technology really will be integral in making us more comparable with other regions around the globe, like California, who has less disease pressure, but more more or less, they're not as sustainable on the waterfront or the soil
Exactly.
health front. So I think this will be really great for the New York wine industry as a whole. And if we have no more questions, I'll let you go. Thank you, everyone, for joining us. Oh, one more question.
Oh, we have one more. Is there an interaction between disease presence and nutrient deficiency? Most likely, yes, right? Like, so we know from a broad level that a plant that's unhealthy is going to be more susceptible to disease because it's less able to activate its defenses to defend itself. So we would guess that there would be some sort of influence on hyperspectral sensing if we have both of these things co-occurring. But what we're able to see thus far is that even in light of co-occurring abiotic stresses, we can detect disease. We could just, the models get more confused, right? So we're working right now to try to add in different information streams to enhance our hyperspectral sensing, right? For example, like giving the hyperspectral data the previous knowledge of like, well, we just had a really conducive period of disease that will help it make a better decision, right? It's like, okay, well, it's more likely to be disease. So the having nutrient deficiency and disease leads to more confusion in the models, but it doesn't fundamentally get rid of the ability that we've established. It still works. The models just get more confused, and we're improving this day by day. Any further questions, y'all?
Well, great. Again, thank you for your time. Thanks, everyone, for being here with us. We
Yeah,
will
absolutely.
have the recording posted up if you're interested. And then I'm sure you can contact Katie if you have any further questions.
Yes, please do.
With that, everyone, enjoy your day.
Thank you.
Bye.